get this thing, maybe. Okay. That look good, everyone? You're okay? Okay, good. So last time we talked about competition in variable environments and, well, not competition, growth in variable environments. And this time we're gonna move on to the topic of the seminar, which is competition. So, but as a sneak peek for next time, we're gonna discuss this paper by Daniel Smith and Priyanka Amarasakare, came out in AmNat. This is, just one of the things on my list of things I want to read. So we'll see how it goes. So I'll email that around. Okay, so let's start off. There are gonna be a few flashbacks to previous lectures here. And we're gonna start off with this idea of the competitive exclusion principle. And we're gonna keep patching this over the course. So don't take this version 1.0 as actually true or anything. But the original version, the competitive exclusion principle, said that you can have no more species coexisting than there are limiting resources. And this gave rise to the famous paradox of the plankton by G. Evelyn Hutchinson. So it was a great paper, got to check it out. And very informal because it was a lecture, I think, that he transcribed. But basically, he said the problem is phytoplankton compete for only a handful of nutrients. They're in well-mixed systems, yet there's many more species than there are limiting resources. So what's up with that competitive exclusion principle? And Hutchinson, and this paper really set off a lot of research in ecology over the next, decades up to now. People trying to find loopholes in the competitive exclusion principle, ways to get species to coexist. Hutchinson himself in his paper solved his own paradox, in my opinion, although maybe some people would disagree. So his idea was that the competitive exclusion principle relies on the fact that competition goes to equilibrium. In a non-equilibrium environment, maybe it doesn't hold, and therefore you can have more species coexisting. And he also made an argument with timescales. So if the fluctuations in the environment are fast, then organisms just experience the average environment. If they're really slow, competitive exclusion goes to completion. But if the time scale of environmental fluctuations is the same or relatively similar to the time scale of competitive exclusion, then perhaps species could coexist. So let's replace competitive exclusion principle 1.0 with version 2.0, which is now that, putting in this caveat about equilibrium. And this was really made clear on this classic paper by Armstrong and McGehee in AmNat, where they talk about competitive exclusion and ways around it. So this sounds promising. But let's make this is a verbal argument. Let's see if it really work out. So the person who's done the most to make this argument rigorous is Peter Chesson. And lots of great ideas from Peter Chesson. One of them is the idea that there are two separate ways that temporal variation can promote species coexistence, two different coexistence mechanisms, which we'll get into today. So one is called relative nonlinearity, and that's going to be a trade-off between growth at high versus low nutrient or resource levels. The other one is the so-called storage effect. This kind of lines up with Hutchinson's original idea that the identity of the superior competitor can change over time and therefore perhaps allow species coexistence. But Peter Chesson is like, well, not so fast. Maybe it's not so simple. Yeah, what's up with these cute animals? We'll see. All right, so we'll start off with nonlinearity, relative nonlinearity. And so here are it's competition for one resource. That's kind of our baseline model. And we see there's the same curves that we used early on when we first introduced competition for one resource. And so we know at equilibrium, species 2 is the best competitor because it has the lowest R star for the resource. But there's these curves cross, there's a trade-off. So we see that, away from equilibrium, species one can grow faster. So maybe in a fluctuating environment, we can make them coexist. So the idea of this trade-off between R star and maximum growth rate, which has also been called by Jim Grover, a gleaner opportunist trade-off. The gleaner is the one that can live at low resources, and the opportunist can utilize high resource abundance. Now, coming back to our discussion of Jensen's inequality, we see that both of these growth curves are saturating, which means that they have negative second derivatives with respect to the resource, which means that really neither species particularly enjoys environmental fluctuations, right? Environmental fluctuations will slow down the growth of both species compared to growth on the average resource. But the functional response of species two is more nonlinear, and so therefore it suffers more. Okay, so that's why I say that neither species really likes environmental variation, but species two, the good equilibrium competitor, it really hates it. Okay. And so then the next stop in this intellectual tradition is a paper by Richard Levins. And Levins had the idea that in a variable environment, we can think of variance in the resource as a resource itself. Okay, that's pretty crazy. But where does that come from? So here's this approximation that we had of growth, this sort of first order Taylor series approximation. So the average growth rate is approximately growth on the average resource plus 1/2 times the variance in the resource, temporal variance, times that second derivative of the growth curve. And so here we can plot zero net growth isoclines for the two species now as a function of two limiting factors, average resource and variance in resource. So dark green, that's our good competitor gleaner species. So if there's no variation in the resource, it's the better competitor, its R star is lower. But as we increase the variance, we see that the gleaner suffers a lot, whereas the opportunist, not so much. And therefore these curves cross. So there's this potential coexistence point, where at least, I mean, we can certainly say that there could be a switch in the dominance, but will they stably coexist? So this is a little bit mind-blowing. It's also, I think, pretty heuristic. It relies on this Taylor series approximation. And the next step is, remember, we got a few other ingredients to talk about coexistence, not just response, zero net growth isoclines, but also impact through impact vectors. So this is where it gets really fuzzy here. But the idea is that both species, by growing, they consume variance in the resource. And this nice review by Yamamichi and Latin that just came out on the gleaner opportunist trade-off makes this point really clear, is that to get stable coexistence, the light green, the opportunist, needs to, oh God, that's backwards. I have to think about it. So needs to consume more of the variance. Yeah, I should have these flipped. But anyhow, that's going to be like sort of a natural result, because when it grows fast, it dampens down environmental fluctuations. Anyhow, let's just remember that you need not only like zingies, but also impact vectors. But how you actually calculate these impact vectors isn't so clear to me. This is more of a heuristic and possibly wrong picture. Okay, so let's get a concrete model here. So this is something that I worked on with Alina Lichman and Colin Kramer over the years. And so this is the most exotic animal I've ever held. So we're going to look at growth in a periodic environment, and we're going to alternate between a good season where things grow and compete, and then a bad season where everyone dies, and they're just going to go back and forth. So tau can be the overall period of fluctuations, and phi is the proportion of each, let's call it, well, each period that growth is allowed in. And this was originally inspired by work that Elena Lichman did, looking at competition in the lab with fluctuating light. Yeah, I'm munching in some props there. But on a longer time scale, it could also be a good model for growth in a temperate lake, like in Michigan, for example, where winter not such a good time. Most of the growth happens in summer. Okay, so that's the setup of the forcing. Here are the model equations. So it's just our standard competition for one resource with Monod functional response in the good season, and then that alternates with periods of exponential death. And so I'm going to call this whole growth function G sub I for a given species. And we'll assume here a closed system. So instead of doing a chemostat for simplicity, we're going to assume that you can just add up all the nutrient in the system. So R tot is the total amount of nutrient, and then R tot equals R available nutrient plus N1 and N2, which is nutrient bound up in the biomass of the species. So we can rearrange that, and then we get this algebraic expression for the resource. This is just a little trick to make things a little bit simpler. So, all right, so before I go, so now this little symbol here means we gotta move to Mathematica and we'll run some simulations. But before we do that, any questions out there?
Is it another way to represent this by like explicitly modeling R through time, like as a sine function or something like that?
Yeah, I mean, you could do that, but we need some way to have yeah, I mean, people have done that. Usually in a chemostat, so there's a whole mathematical literature of competition in the chemostat where, say, the input rate or the dilution rate fluctuates periodically. There's a whole literature where people, instead of applying nutrients continuously, apply them in discrete pulses. So there are a lot of different ways. This is just one of them. So, all right. Other questions on the setup?
I was wondering about this variance as a resource thing and because that also kind of helps to answer the paradox of the plankton thing too, right? It's variance itself. I don't know, it's just
Yeah.
it seems so exotic as an idea.
Yeah, that's why it's mind blowing. So that's the idea, yeah, is that maybe we can think of variance as a second resource and then we can get coexistence. Now, I guess based on that logic, maybe we should only get two species coexisting through relative nonlinearity because you just have average resource and variance.
Yeah, but then you have kurtosis and everything. You can get
maybe.
however many you want.
Right. Yeah, right. So it's just an approximation. So maybe higher order moments come in. But yeah, anyway, I mean, it's interesting. And it'll lead into Peter Chesson's analysis of these mechanisms. But I don't know, it's also a little bit heuristic too.
Is just kind of following up on what was just said there. Is it known that you can get an arbitrary number of species with a kind of complicated enough fluctuation, or is that?
Yeah, it's known. There's a apocryphal master's thesis by Ziccarelli from 1975 that showed this. I've never laid my hands on Ziccarelli. But yeah, that it's true that you can get arbitrary number of species coexisting on one resource through relative nonlinearity. How easy it is, how biologically realistic the parameter values need to be, that's another question. And I think in that case, probably the consensus is it's really easy to get two species, very hard to get more. So, but that's just kind of a rule of thumb. All right, other thoughts before we have a peek at this? So I'll share this.
Oh wait, I will say there was one person who wasn't holding an animal. I know this is being recorded, so maybe you want to be careful how you reply, but does that say something about their character or what?
Yeah, I mean, yeah, it's a little bit. I mean, it's a little bit random. Like I mean, it's a famous picture of Hutchinson. There's another one of him like posing with a giant tortoise I could use. And then I found that one of Peter Chesson, but Peter Chesson's from Australia, so it makes sense. And then like I wasn't gonna include like Michi's paper, but then when I was Google Scholar, I'm like, he's holding a freaking koala. So anyway, yeah, I'll write Anderlecht and request a picture of him with his most exotic animal to update the slides. All right.
Actually, can I weigh in with a quick question?
Sure.
This might be really dumb. But would this competitive exclusion principle type reasoning apply to cases where, say, you have a species radiation where they're maintained in sympatry due to like mate preference? So they're ecologically undifferentiated. The only reason they're different species is because they're not interbreeding with one another.
Right. Yeah, that's a great question. So there's two parts to it. So first, I think, in general, the competitive exclusion principle is kind of an ecological upper limit on number of species that can coexist, and that will be hard for evolution to work its way around. So it's pretty generally true. But when you start talking about, then you raise the issue of like reproductive isolation. I mean, reproductive isolation to make them good species, that's one thing. But if there's like reproductive interactions between the species, like maybe they're interfering with each other's reproduction, or there's some kind of LE effects, then maybe it gets more complicated. We could have a session on that. I'm sure we could find some papers on that. Okay. All right. So let's look at this relative nonlinearity model. And yeah, looks pretty good. Set up the model. And okay, so here's the forcing function, just as we described in slides. And here's two growth curves along with their mortality rates. So we see that these species show the gleaner opportunist trade-off, and there's relative nonlinearity. So just like before, dark green is going to be our good competitor, our gleaner, light green, the fast-growing opportunist. All right, so let's run some simulations and see what happens. Two parameters. Our tote is the total amount of nutrient in the system. That doesn't actually do a lot here. And tau is the period of forcing. So we're going to start with a period of 10. And then what we're going to vary is phi, the proportion of each period that's suitable for growth. Okay, so start off with 100% good season. And we see that dark green, the good competitor, excludes the fast growing light green. Makes sense. Now let's make each year 60% good, 40% bad. All right, so now you see that the populations fluctuate over time. There's this like very rapid variation in the populations, but again, the opportunist goes extinct here. But maybe it held on just a little bit longer. Let's see. Really dial down, so only 25% each period is suitable for growth. And this isn't a rigorous demonstration here, but sure looked like both species are managing to coexist over time. And if we make the growing season a little bit shorter, then we see that in fact this leads to a flip in the outcome. So the gleaner is excluded and the opportunist wins, because it's like you're up north in the Arctic. There's only like 2 months of like growing season here, so you have to grow really fast if you want to survive up there. Okay, so that's our first
I have a
set
question,
of simulations.
Chris.
Yeah, sure.
So the one above where you said it was pretty much like coexistence, I mean, like, yeah, that one. So like if it's like so volatile, like it's like, like it's really fluctuating really fast, like given the time scale, like, is that truly coexistence, or like it just kind of depends on like the species, I guess?
Right. Yeah, I would say, I mean, we'll test later on, I think, to see if it's true coexistence. And what we mean by true coexistence here is that they would persist arbitrarily long on this, attractor where they both have non-negative densities or non-zero densities. And we could test that. We'll get into later. We can test that with the mutual invasion criteria like we talked about before. So, just running the simulation, we can't say for sure, but seems like, of course, the fast growing light green guy took over first, but then the gleaner managed to like crawl back in and join. So I have a feeling this is like bona fide stable coexistence, but with fluctuations, right? It's a non-equilibrium kind of coexistence. Yeah, Sarah?
Maybe I misunderstood. I just want to check if I'm on the same wavelength in terms of vocabulary. Maybe for this part of the next one, can you go down the next one? It's a bit easier for me to explain what I want to say. Here you were saying that the lighter green one is a fast grower. In my mind, I associate the one with having a lowest R star, the best competitor, but it doesn't necessarily mean it grows faster. It means that it has the ability to grow when resource is most limiting. And then in addition of having this gleaner opportunities trade-off, there is fast, slow grower. I mean, it was kind of two levels that could intertwine. Do I have a confusion here? Like, well, if we could just check.
Yeah, maybe it's just terminology. So sometimes, we can talk about the gleaner and the opportunist. So the gleaner is the one with the lowest R star who would win in a constant environment, the dark green one. The light green one, the opportunist, has the fastest growth rate in a resource-rich environment. And so sometimes I'll just call the gleaner, my name for that is good competitor, which is as short for good equilibrium competitor, perhaps. But as we see here in this very like seasonal environment, it's actually not such a great competitor because it's getting itself excluded here. So yeah, I guess it's just I should be a little careful about how I call them.
And also, like in our field, when we say fast grower, it usually means larger maximum growth rate. It doesn't mean it's always faster in all the environment.
Right. Yeah. Yeah. So this one is certainly there's that trade-off. So the light green one has the higher maximum growth rate. And it grows faster up to this crossover point, and below that, the gleaner is better. All right. Any other question on this first set? All right. Okay, so let's now get back into the middle there. And now let's just make the period longer, right? Because these have been pretty fast fluctuations. So here's a baseline case where the fluctuations are, again, period of 10. And for this particular value of phi, we see that the gleaner is winning over time. Now let's just make the period longer, okay? And keep the relative proportion the same. This is just looking at the dynamics over the last period. So here, all right, so now we made the period a little bit longer. Now we seems to have stable coexistence over time. And if we look at last period, we can see that fast grower dominates in, let's call it spring. The gleaner dominates later in summer. Then winter hits, they get reset. So this is an example of stable coexistence. And if we really crank it to a period of 300, again, it looks like stable coexistence here. The dynamics are getting like more large amplitude and abrupt, but again, they coexist. So this is partially addressing Hutchinson's hypothesis about the period of fluctuations. And so far, it looks like, Hutchinson was not correct. because here we have like slower and slower forcing. It seems like they still manage to coexist. Probably the resolution of that is there's some minimum viable population size. Once you get below, you're actually extinct. So there's longer periods where these guys are down there at super low abundances. But so far in this perfect deterministic world, coexistence seems easier for large period. What is this last thing here? Okay, all right, that's good. Let's pop back to the slides. Now, let's see, are there any questions on the second set of simulations?
How does this relate to the thing that you and Elena did, or is this a little bit separate?
I would say this model is pretty similar to the model Elena and I used. Ours is slightly different because we were talking about competition for light, but it's essentially the same thing. All right, so that was just some simulations. How do we actually nail whether they coexist down in a more rigorous way? Well, invasion criteria, as usual. So 2 steps in this analysis. One, we need to solve for the resonant dynamics. In this case, a periodic forcing it's a resonant limit cycle. So that's this first graph up here. So I put in species 1 by itself. You see that early in spring, it grows up to high abundance, sucks the resource down to its R star, stays there till winter hits, resources get regenerated, and abundance of the species goes close to 0. So this is step 1, resonant limit cycle. And obviously we have to do this numerically. It's a little bit touchy, but there's some numerical tricks that once you learn those tricks, it's not the worst thing in the world. Then once we have this resonant dynamics, we integrate the growth rate of the other species over one period. So this is what we learned about averaging growth rates, right? And we simply average the instantaneous growth rate of, in this case, the gleaner trying to invade the opportunist. And so this bottom graph shows the instantaneous growth rate of the gleaner over time. And early in the season, when resources are still abundant, it's growing as fast as it can, gets a little boost there. Then when the opportunist reaches its carrying capacity, the gleaner is still trying to break in, right? Still the positive growth rate because it's a better equilibrium competitor. But then winter hits and then it dies off again. So the real measure of fitness, invasion fitness here is we just integrate this over one period, do that numerically as well. We have value that's a little bit positive. So therefore we can say that species 2 can invade species 1. And we could flip it around and do the same for the other. So this is, pragmatically in a numerical way, how you calculate invasion criteria. And then, well, any questions on that? All right, and so then we can do this twice, do it for each species by itself, and then we can use this invasion criterion to map out the outcome of competition. Here is a function of the phi proportion of each year that's good, and the period of forcing tau. These are different parameter values that I was showing. But basically what we see is that for long growing seasons, the good equilibrium competitor, the gleaner, wins. For short growing seasons, well, really short, they both die because it's just too short for both of them. For a little bit longer, the fast growing opportunist wins. And then we have this coexistence zone between them. And for slow forcing, coexistence region's pretty wide. For fast forcing, it really kind of zooms down and almost disappears. Yeah.
Sure. So the invasion analysis, does it depends on the initial abundance of the two? Because they kind of didn't reach. Because if you do the analysis for equilibrium, you wait until longer enough, so the initial condition probably won't matter
Right.
that much, but.
Yeah. So the question is whether the invasion analysis depends on initial conditions. And as long as the resonant has like a single, like globally stable attractor, then it shouldn't. So that's step one here, solve for resonant limit cycle. And the trick that's involved in doing this numerically is we're trying to find, values for the resource and the abundance of the resonant species such that at the end of the period, they're at the same place they were at the beginning, right? So that's how you do it numerically. Can be a little bit tricky because these are getting like really close to zero, but if you're careful, you can do it. Right, and so once we have those
Chris?
invasion criteria, we can use it to draw these lines on this outcome graph. Yeah, Veronica?
So just thinking about like migratory, like birds, for example, like they leave because it's a bad season.
Mm-hmm.
So like how does that work? Like when a migratory species is kind of like moving from like I don't know what their home really is. Is it like, is their breeding area their optimal and then they're moving and so in a sense they're kind of shifting to maybe a suboptimal place when they are like in a non-breeding season, for example, and then it like, do you think like they kind of shift along the gradient as they're
Yeah, so that's a great question. So I mean, I should say in this model, these guys are so dumb, right? They're just like, trying to grow and then they die and that's it. So there's all sorts of ways that smarter organisms might, adapt to these environmental fluctuations and try and increase their fitness. So for phytoplankton, that could be like, at the end of the season when nutrients are low and it's starting to get cold out, maybe they form resting stages and go into like sort of hibernation mode and then wake up in the spring. So that would be one example of some sort of like more plastic response. And I think what you're saying about migration would also fall into that category of organisms, adapting to environmental variation. Probably such models exist. I don't know how they work, but I guess that's requiring like space and time, right? Because they're moving around and fluctuating environment. So it's probably more complicated. But I think it could be done.
Yeah, it was like making me think if maybe there's like a trigger point where like a sweet spot among the proportion good season, and then it's like, oh, time to move,
Yeah. I think if they were like, a little bit more adaptive in their decisions, that might promote coexistence, but maybe not. Remains to be seen. All right, so that's what I've got. So this is relative nonlinearity. You can see here, as long as the period of forcing is sufficiently large, there's a pretty wide coexistence region here. So I'd say this is a pretty robust mechanism of coexistence of two species. As I mentioned earlier, in our experience, it's very, very, very difficult to like slip in a third or a fourth here. It requires just unrealistic trade-offs. So yeah, relative nonlinearity. Any questions on that?
So do more than two species coexist when you have a fast forcing in this case?
Yeah, I think fast forcing is just going to be uniform. My feeling is fast forcing is going to be uniformly bad for coexistence. And we have some arguments in this paper. We did a sort of averaging argument where if the fluctuations are sufficiently fast, then abundances don't change very much over the course of a period. So essentially, organisms just experience the average growth rate over the period, the average resource over the period. And so that, leads to sort of a competitive exclusion. All right, so that's mechanism one, relative nonlinearity. Let's look at Chesson's second temporally varying environment coexistence mechanism, what she calls the storage effect. And I should say, like, the way Chesson explains all this is much more general. I'm just going to give you the version that's kind of specific to resource competition. So it deviates a little bit from the language he uses, but I think the spirit is essentially the same here. So we've seen this graph as well. So the idea is that there's some environmental factor now, perhaps temperature, which species have a trade-off. So species one likes low temperatures, species two likes higher temperatures. So for a constant environment, there's a switch in the identity of the superior competitor. And so now the idea is, following Hutchinson, we'll make the environment vary back and forth across this border. And, species one will be best for a while, species two will be best for a while. Each year, maybe they'll coexist. That's the idea. And so we'll do an example with sinusoidally varying temperature. There's a sine wave. And here I'm just showing the optimal temperature for the two species that we'll have in our simulation. So hopefully I kept the colors straight. So the gold one likes it warm, blue one likes it cold. All right. Okay, so we're back here. Ignore that, it's a mess. And I should say this model is even simpler because we're going to just go with a linear functional response. So we don't have Monod, we just have linear functional response. Pretty simple. Now, here's a wrinkle. There's two things that could vary with temperature. Either a species maximum growth rate or growth rate, let's call it mu, could depend on temperature, or their mortality rate could depend on temperature. And either one, we can set up the situation so that there's a switch in the identity of the best competitor. So let's start out by making it temporally varying temperature-dependent death rates. Okay. I'm just going to make the death rates be some kind of quadratic function of temperature with each species with an optimum. Here's their mortality rates as a function of temperature for these two guys. So, and everything else is equal. So you see that there's a switch point around temperature of 0.1. Okay, so for lower, blue's better, higher, yellow's better. And we can plot the R star as a function of temperature. It looks basically the same. So we see that there's this crossover point. So now we can just run some simulations and see if Hutchinson was right. Can we get these species to coexist in a variable environment? Well, first, let's check the constant environment. So if temperature is 0.4 and constant, yellow wins. If it's 0 and constant, blue one wins. And if it's right at that crossover point, it looks like it's neutral because they have equal R star at the crossover point. So now, variable environment. Here's the variable environment. And what we're going to tweak, well, let's just simulate this and see if they manage to coexist or not. Doesn't look so good. So it looks like the blue one outcompete the yellow. And you notice I've got this a little bit asymmetric so that the average temperature is 0, but the yellow one's optimal temperature is 0.4, but the blue one's is minus 0.2. So it's a little bit favoring the blue one based on the averages here. So they didn't coexist. What the heck? So now we can maybe we could adjust the optimal temperature of the blue species and get them to coexist. So now we make blue a little bit colder relative to the average of 0. Oh, now the yellow one wins. Maybe make it really close. And, in terms of the symmetric variation, no. Looks like whoever's closest to the average temperature wins in this situation. The only case we might come up with is if they have identical, like plus or minus 0.4 when the variation is around 0. And they coexist, but maybe in a neutral way. So basically, not looking good for Hutchinson's solution of the paradox of the plankton. In this variable environment, it's really hard to get species that coexist.
Wait, but their thermal performance curves shape is identical as well?
Well, their thermal performance curves here, the thing that the environment affects is their death rate, right? Which is assumed to be U-shaped.
But they're like the same formula.
Yeah, same formula, just with different optima. And everything else equal about these guys.
Hey, Chris,
Yeah.
would it be cheating to say that coexistence would just depend on scale? Because like, let's say like there's like a mountain or something and the temperature is different by elevation. So maybe if we just say that and they coexist on the entire mountain, then we're good? Or is that cheating?
It's not cheating. It's a great idea. But in this case, we don't have a mountain. We just got this one spot, right? So if we had like a spatial gradient, then probably we'd have to check it out to make sure, but it seems reasonable. But this is talking about like just at this one spot, closed system.
If I can bounce back on that, I like this idea of like maybe cheating, because in this whole lecture, I keep thinking of like the time scale at which we consider coexistence. And I think it depends on the type of organisms we have and if the fluctuation is something that is recurrent and will come back or not. Because for some phytoplankton species in the lake, not that I know all of them, but some might actually be at the same place in the water column for a very small amount of time.
Mhm.
Does it mean that they're not coexisting at that same amount of time, or like that time point? Probably yes, but for the long term of the whole year, maybe we say they don't. And I think it's interesting to just maybe
Yeah.
have that in
I
mind.
agree. That's a great observation. In the case of a non-spatial model with periodic forcing, it's sufficient to show that if each species can rebound from rareness over one period, that's sufficient for coexistence, modulo all the problems with invasion criteria.
Yeah, just to jump in on the same. So in the previous example we saw with the increasing periods, one thing to note, exactly. So one thing to note here is that as the period gets longer, the actual temporal overlap is getting smaller. So they are on the scale of the entire period, they're coexisting, but the longer the period gets, the more partitioned that period is becoming into like who is there. So there's like temporal alpha and beta diversity that is changed.
Yeah, that's right. So you have to, and so it is scale dependent. And usually for species coexistence in long term, then it's determined by the largest temporal or spatial scale. And we have to think, how that matches up with, conditions in the real world. At least in the mathematical, pure sense, that's the right definition. Well, anyway, in this case, looks like having there's no storage effect with temporally varying death rates. There's no stable coexistence. And you can show this. You can show that this is in fact true. Whoever's on average does best. So maybe Hutchinson was wrong. There was an early paper by Huntley and Chesson, which sort of gave that impression based on such analysis. But what the heck? All right, let's just look at temporally varying birth rates instead. So now we'll make the maximum growth rate a function of temperature, and let's make it a Gaussian unimodal function of temperature. And now the death rate will not depend on temperature. So we can plot the birth rate as a function of temperature. And we see there's similar trade-off where species have different optima. There's a crossover. We can compute the R star versus temperature. We see that they intersect pretty similar to before. So maybe we're just setting up the same thing in a different way. So there's a switch in competitive who's the best at temperature 0.1. What happens now? All right, so now we're gonna just stick them in there. Again, it's the average temperature in our forcing is gonna be 0. And the crossover point is at 0.1. So one of the species has a little bit of an advantage here. Maybe they will not coexist. Oh, they did. Looks like they're both, pretty clear. Blue one rebounded from rareness and they're coexisting. All right, so let's just move one of the species around a little bit, make them perfectly symmetric around the average. Oh, they look, perfectly symmetrically coexisting here. Let's make the environment a little bit more favorable to the yellow species. Yellow species has a higher average abundance, but they're both still, pretty happy in coexistence here. So this is a, radically different outcome than we had in the first example with the temporally varying death rates. We can just tweak this a little bit, look at the effect of the period. Here's a longer period. Here's a faster period. In all cases, here is even a really short one, a super short one. All right, that was too short. So that's too fast. They didn't manage to coexist when the period was 0.1, but in general, pretty robust here. So interesting. So any questions on that before we go back and do a little analysis to figure out what's the difference?
I do find it strange because birth is an addition, right? And then death is a subtraction of some sort, but
Yeah. Well, it's going to turn out it's all going to be about multiplication. So, let's see. All right, so we're popping back here. All right, so here's the analysis. This is the essential analysis that Chesson does with the storage effect. All he does it in a more general term, looking at competition versus including a resource. Okay, so here's the model, growth of each species. So change in abundance of species I. There's a linear functional response on the resource minus death times the abundance. So we can scooch the abundance to the other side and get the per capita growth rate on the right. And then what we learned last time is the right thing to do in a periodic environment is to average the growth rate over one period. So this bar on top indicates a temporal average. So the average growth rate over one period is the average per capita growth rate on the right-hand side. And we can, by some of the rules of averages, we can just break this up. So we have the average of mu times r minus the average of n. Okay. This key here is that what's going on there. All right, so now let's look at the situation where there's only variation in the mortality rate. So when there's only variation in the mortality rate, that means that the mu's, the per resource birth rates, were constant. And so then that's just a number. Get rid of the bar here. And what we end up with is essentially something that looks like resource competition where they're competing for the average resource R bar, right? So it's like the average growth rate is your birth rate times the average resource minus your average death rate. This is basically an R star kind of model. And so just like, with R star models, coexistence is impossible. Whoever has the lowest average R star will win competition. So this kind of explains why we didn't see coexistence when there was temporal variation only in the M's. Okay. Now let's flip it around and look at where there's temporal variation, not in the M's, but in the mu's. Okay, so going back to the same starting point, now M is a constant, so we just replace it by number. But we still have this average of a product, right? And this is I don't know, a fact from probability theory, is that the average of a product is equal to the product of the averages plus their covariance, right? And so this isn't even an approximation like that Taylor series we did before. This is just like exactly true. So now it looks like the growth rate of each species has this extra term, covariance between their performance, mu, and which varies over time, and the resource abundance, R. So it's like, again, there's competition for the shared average resource, but maybe each species gets a bonus in the form of this covariance. Let's see. Right, so what's the difference between these two where the variation comes in? The first case where the variation was in the density independent term, the mortality, it doesn't generate this covariance between performance and resources that's required for the storage effect. So this covariance term here, this is basically the real, if you had to boil it down to one thing, this is the essence of the storage effect, this potential covariance. So when the density independent bit doesn't fluctuate, you don't get that covariance, so there's no storage effect. But when there's variation in the density dependent bit, in this case, the birth rate, you do get this covariance. And so, yeah, interaction between resource dependence or the strength of competition and environmental variation is really the key to the storage effect.
What exactly do we mean when we say storage effect here? Is it like a Drude model, or is it like something else?
Yeah, thanks for asking that. It's a historical name, and I think it has nothing to do with nutrient storage. What it has to do with is originally when Peter Chesson was working on this, he was working, like his baseline were annual plants. And in the case of annual plants, every year the population resets, and he showed that with strictly annual plants, environmental variation does not allow coexistence. You need a long-lived life stage, which he took to be resting dormant seeds to make this mechanism work. So starting from the perspective of annual plants, you need this long-lived life stage where you can sort of store your gains from like when the environment is good. So that's why it's called the storage effect. If your baseline is something more like continuous time resource competition model, that's already built in. So you don't need the special extra, you don't need to mention it because it's already built in. So it's a bit of a historical accident, I'd say.
And the thing you're storing in that case is just like your species abundance. Like
Yeah, exactly.
It's good.
Yeah. Yeah, you need some way that when you have a good period, you can stash your success and then kind of weather the bad period in a way such that your mortality rate is lower. And that generates this covariance between competition and the environmental variation. All right, so now since this is theory seminar, we're just going to delve just a little bit deeper into the Chessonian mindset. This is pretty cool, actually. Okay, so we've seen already that you can decompose growth rate into growth on the average resource, covariance between your environmental response and the resource, and mortality. But there's still a little bit hand wavy, this argument here. When are we going to do this? We're going to do this in particular when a species is rare and invading. So we're going to do this sort of decomposition of growth rate on the invasion rates. So that's why I'm denoting now lambda inv and res. This is the growth rate of a rare species inv trying to break into the periodic temporally varying environment set by a resident res. So here's our decomposition. I'm assuming the variation comes in through mu. It's just following like before. So basically, we can do this for the invader invading the resident. We can take its invasion growth rate and break it up into 3 terms. Average growth on average resource, covariance between growth and the resource, and mortality. And technically, we could do the same thing for the resident as well. We know that the resident's growth rate into its own environment should be 0 because we are assuming it's gone to its long-term attractor. But the second, thing should also hold true. So let's try and do this decomposition. And remember what I was saying is this covariance term here. Each species has their own, you see, they're species specific covariance. So maybe they each get a benefit, and this is going to allow coexistence. So let's just do this decomposition. So here we're going to look at this case where period's 100, they're coexisting pretty robustly. So here we're finding the resident, we're putting in species 1 as a resident, 2 is absent, finding the limit cycle dynamics of species 1 by itself. So here in blue, this is the abundance of species 1 over a period. And green, this is the available resources that it leaves. Okay, and you can see that again, there's a good limit cycle where the endpoint is the same as the starting point. So this is the resident environment. And now we can, what's this next thing? Okay, all right, so this is plotting make this a little bit smaller so we can see better. So this is plotting then the environmental response of the 2 species. Blue being the resident, gold being the rare invading species who isn't here. And so what you can see here is that when the resident is doing poorly, resources are abundant. So at this point here around time 30, it's really bad weather for the resident species, and its abundance is declining and available resources are increasing. And then later on, when the resident is performing well, then its abundance is high and resources are limiting. They've sucked out all the resources. So basically, the resident is inhibiting itself because whenever it's a good season for itself and wants to capitalize on its growth rate, resources are short supply. So this is that covariance between resources and performance. Okay, so let's look at the growth rate of the resident invading itself. There's a little warning, and the average is essentially 0, as promised. So the resident can't invade itself. But now let's do this partitioning on it. So we can calculate the species 1, the resident's average growth rate, mu1, per resource growth rate over a period. This is the mu bar, 0.39. We can calculate the average resource over the period. It's somewhere like around 1, so somewhere in here. And finally, we can calculate the covariance between species 1 performance and the resource. It's negative. So when we add it all up according to that formula before our decomposition, indeed, we recalculate 0 here. So the resident has some positive average growth on average resource, but then in fact, this covariance term penalizes it. That's this minus 0.275. Subtract off the mortality, add it all up, it comes up to 0. So this is the resident against itself. How about then the invader against the same resident? So the invader, species 2, trying to break in, has a positive invasion fitness of 0.33. That means it's doing well. Its average growth rate over the period is 0.4. So those are the first two terms. But its covariance between its performance and the resource is positive. So this is the bonus. And if we add these things up again, this decomposition of the growth rate, we recapitulate its actual growth rate. So it's a little bit more confusing than you thought it would be, I think. So what's confusing about this is the fact that this covariance term that we thought was the storage effect benefit, well, the invader gets the benefit, the resident actually gets a penalty based on this covariance. That's a little bit weird.
I think it also makes sense because the residents would alter the environment it lives in because it consumes the resource. So they should have a like negative covariance.
Yeah, exactly. So I mean, it makes sense when you think about it, but I was a little bit surprised that it works out like this at first. So this gives rise to one last cool trick from Peter Chesson to like try and like straighten this out and align this a little bit. We can rewrite the invasion growth rate of the invader. We can subtract 0 from this. You can subtract 0 from anything and nothing changes. And there's a particularly nice form of 0 right underneath it, which is the resonance growth rate into itself. So we'll just subtract our res from our inv-res and collect the terms. And so this is a nice way to like do basically what's called a resonant invader comparison. And we can rearrange it, scooch it around. So every term in here is a comparison between the performance of the invader and the resonant. So this first term is the comparison of their average growth rate, average performance, right? The second term, this is now the storage effect bonus that the invader gets. But now you see that bonus is relative to the penalty of the resonant. And finally, we can compare their mortality rates. So this rearranging is, one of the keys, see, John, to Chesson's thinking. So whenever in Chesson's papers about the storage effect, you don't just see the covariance between what he calls the environment and competition. It's always delta covariance between the environment and competition. And so that delta is this comparison between the invader and the resonant. And that's nice because each one of these terms you can interpret as an ecological mechanism. And the only one that will lead to coexistence here is this one in the center, this covariance. So yeah, so that's a little bit of background info on coexistence in variable environments. Relative nonlinearity, pretty good for getting 2 species that coexist, really hard to get more than 2. The storage effect is much more robust. You can get easily more than 2 species coexisting with the storage effect because every species has their own little covariance term that might help them out. But it's not automatic, right? You still need the right requirements. You need this interaction between competition and the environment for the storage effect to work. So that's my background info for next week's paper. Any last questions on this?
About multiple species. So like using this invasion analysis, like this decomposition.
Right. Yeah. So I mean, I should say it's kind of all the rage, has been all the rage in competition theory, modern coexistence theory. The idea is that you can partition, invasion growth rates into distinct ecological mechanisms. And then you could use this to compare different species in different ecological situations. But it's not so straightforward. I mean, another wrinkle here is that if we ran the same partitioning, it would depend on who was the resident and who was the invader. You would get different numbers here. So that's just the beginning of the problems. And then what you bring up is like, well, how do you extend this decomposition to more than 2 species? Well, we saw back with Lacca-Volterra, right? Even going to 3 species is like pretty, gets pretty out of control fast. So I think it's an open problem. In the cases where, this is done theoretically, often people choose very idealized symmetric models so that each species responds, to the environment in the same way on average. And then you don't have those problems. So yeah, there are limitations when moving to more than 2 species. I think it still needs to be sorted out.
You cannot do invasion analysis on 3, right? 'Cause
Well,
what is the starting point? Like, it doesn't need to be 2 already coexist.
Yeah, exactly. That's one of the problems with invasion analysis on more than 2 species is you need to like start with a 3 species coexistence point, remove 1 species and see if they can rebound. That works fine if all the pairs can coexist.
Right.
But if one of the pairs can't coexist, what are you even calculating? So it's an issue.
I think something is in the chat.
Yeah. All right. So I'll stop sharing this and attend to the chat. Oh,
Chris, I have a question.
yeah.
I think in the beginning you had mentioned a paper by Letton where they were showing various sensory resources. Maybe I missed this, but how does that link directly to the way Cheston's treating storage effects? Because the way I understand the storage effects is you're looking at the covariance, right? But the way Letton handles this is he's adding variation in the resource itself. So it's almost like a pulse or something like that.
Yeah. So in particular, of course, he's done a lot of work. Andrew Letton's done a lot of work in competition variable environments. So the thing in particular I was referring to was just a review paper where they were focusing on relative nonlinearity as opposed to the storage effect. So I think, the resource pulses would be another example where relative nonlinearity could be the main force. But mostly I just wanted, that picture of Yamamichi with a koala.
Chris, can you talk a little bit about the sort of differences or how to tell apart relative nonlinearity from a storage effect? Because in both cases, it kind of seems like, okay, the environment's varying to sort of a condition that's favoring one species to the condition that's favoring the other species, and this is leading to coexistence. Like what's the sort of distinction?
Yeah, that's a great question. I think, myself, I just take the variation. If the variation is in the resource, but not any other environmental factor like temperature, I think of that as giving rise to relative nonlinearity. And then mathematically, that's going to be characterized by the variance in the resource, right? As a factor in the invasion criteria. Whereas if the something besides the resource, like temperature, varies, or growth rate aside from resource varies over time, that's more the storage effect, especially if it gives rise to that covariance between the environment and competition. Probably for a given model, you could have both acting at the same time. And then, you can use some Chesonian decomposition techniques to parse out the importance of the 2 different mechanisms. There are probably other mechanisms besides there, but it's a little bit hard to think about. So it's a way to subdivide. Whether it's useful or not, that probably depends on case-by-case basis. I should say, these decomposition of growth rates, they don't actually usually help you calculate anything, right? They don't help you figure out whether a species can invade or not. You can do that by just, doing the appropriate nonlinear averaging. What it is a way to like interpret your results. So it's more heuristic importance, I think.
Thank you.
Do you know
All
of
right.
any papers that have used like a more like a Zinji approach, but to explain storage effects? I've tried to see it in the literature, but I don't think I've seen like a Zinji approach to it.
Yeah. There's one paper I cited in here with Elizabeth Miller and myself. It was more evolutionary. We looked at a 2-season model where there was just temperatures fluctuating, alternating between two values. In that case, you can break it down into like average resource in one season, average resource in the other with zero net growth isocyclines. But moving beyond that, I think it's impossible.
Maybe you could plot the density distribution of Zinjis over the seasons for 2 species and use that to calculate something. I'm not sure how helpful it would be in the end, though.
Yeah. You can report back if that has any legs to it. All right. Any last thoughts on this background? All right. Well, we do have a paper to discuss, not much time. So I'm just going to move you all into breakout rooms real quick. So the paper was this nonlinear averaging by Joey Bernhardt et al. And we'll just real quick, I'll share the highlights of it. So we'll just have just a couple minutes where we can compare notes and then come back. So this is this paper. It's an experimental paper. There's along with some modeling. So there's a nice figure in the supplement saying what they did. Basically, they measured static thermal performance curves for a species in the lab, and then did experiments, putting them into fluctuating temperatures in the lab and seeing what predicts better, nonlinear averaging or just response to the average temperature. Based on that, then they did the same sort of analysis using existing thermal performance curves and seeing how that affects the distribution of species in the real world. Here's the big conclusion, I think, of this paper, the one that's experimentally based. Top graph shows a static thermal performance curve in the dark color there. And the dashed line then is the predicted thermal performance curve in a plus or minus 5 degree fluctuating environment based on nonlinear averaging. And then when you do the experiment with the fluctuating environment, you observe these growth rates in yellow. They seem to follow the nonlinear averaging Jensen's inequality rules. So here are some questions that you might discuss for a couple minutes in the breakout room. Is this important? Is the model good enough? And there was also a critique by a couple of people of this paper. What do y'all think about that? So I will just move us now to breakout rooms, discuss for 5 minutes, come back, share a few notes, and then wrap up.